In this video, I'm going to show you how to run GLoads in Abaqus and interpret the results. So we've run a modal. Now we're going to look at a GLoads on this component right here that could be placed on an air vehicle or a car or something like that. It really doesn't matter. What does matter is how to set this up. To do that, you want to go to Step. You want to create a new step called, we're just going to call it GLoad step. We're just going to call it downward GLoad step. And it's going to be a general static procedure type. And we're going to keep all these defaults. We're going to keep this analysis linear. So I'll press OK. So we want to generate some outputs so that we can interpret the results. So if we go to our field outputs, it's already created a field output for this downward GLoad step shown here. We want to just go in here and edit some of these variables that it's going to output to the ODB. So we're going to, we want stress components, we want a von Mises stress, and we also will take displacement as well, and reaction forces and moments. We also want to, one of the things I like to check on these GLoad analysis or gravity load analysis is I like to validate my model by getting the reaction forces and comparing it to the weight of the model. So we want to go to history output. It's already created one for us in the GLoad step, and so I'm going to edit the outputs. I want to get my boundary conditions set. So RPBC is what I call it, and that was shown in the previous video, and I want to return the reaction forces, specifically RF1, RF2, RF3, my vector components in my Z, X, and Y directions. And we'll go ahead and rename this GLoad BC. So we've created our step, we've gotten our field output set, our history output set. Now we actually want to go apply the loads. So we'll go in here and we'll do create a load. We want to create a downward GLoad, and you can make upward GLoads, lateral GLoads, whatever you want, forward, aft, but you want to go in here and you want to select gravity. And we had gravity in units of inches per second squared, so we want to enforce our gravity load from our global axis right here. We want to put a downward load on it, so that'd be component 3, and we wanted to use negative 386.1 inches per second squared. You'll see that it puts a acceleration vector there in the direction that we applied it. So now we pretty much have our job set, or our analysis sequence set. So now we want to create a job. And before I do that, I just want to go back into step, and I want to turn off my modal because it's not, we don't want to look at that. In this case, it'll just extend our simulation time. So if you go in here to Job Manager and you want to create a new job, GLoad job using Model 1, we'll keep the defaults. And so after we've created a job, we submit it, and it'll take a second to run. So it's completed. Now we can go look at our results. So here are our results for our GLoads, and like you see up here, we have our field outputs. We want to look at stresses specifically, and it shows our worst case stresses right here. But we actually want to go into our results up here and go to section points. So right now our thickness of our shells is made up of section points, and it's returning the bottom section point. We actually want the maximum section point. So without going into too much detail, envelope is that option that goes and looks at all the section points across the thickness of the shell element, and it returns the maximum value, the minimum value, whatever you select. In this case, I'm going to select max absolute value as a first order analysis. So I press OK. You can see here it says envelope max absolute. So now we're returning our von Mises stress at our max absolute value. The next step we want to do, that I like to do, is I like to compare my reaction forces to the weight of the model. Since we're using a unit GLoad, it makes it pretty easy. We just compare the response at the boundary conditions to the weight of the model. So to do that, we can go to this create XY data, history output, and since we did a downward GLoad, we want our RF3. I'm going to save as, and I want to sum the reaction forces. And I'm going to name this BCRF3. And it'll return a plot. That's not really important, but it does return, in this XY data column, returns the data points. If you go to edit, it returns the sum as a total of 6.16 pounds force. So this is where I go into my post-processing, and I already created a row right here, boundary reaction forces. The total is 6.16228 pounds force. Now I want to combine that to compare that to the total mass of my model. To do that, I go into the DAT file for GLoads, edit that with Notepad. So this DAT file was generated after I ran that GLoad results, and you go down here and it'll have total mass of the model right here. So you want to copy that, go back into Excel, and then take that value and multiply it by gravity. In this case it's 386.1, and you can see that the mass of the model and the boundary reaction forces in the Z direction are identical. That means we did our analysis correct from a unit GLoad perspective. So now what we want to do is we want to extract our stresses. So I already have a tab set up called GLoad Structural, so we're going to evaluate the structural integrity of the components, the frame and the cover, for this load case. So what I have here is I have the component, the material, the load type, the GLoad scale factor, which I can change. That's a design variable. The ultimate tensile strength, the yield strength of the material, and then I also have the max von Mises stress and max principal stress, which I have to get from FEA. So that's what we're going to do in this case. So what I like to do is I actually like to go into our GLoad ODB here in the model tree and then go to materials. So I'll right click and select replace, and it'll show my worst case von Mises stress of 377 for my frame right here. So I would take that and put it in my spreadsheet for post-processing. And then I also want to look at my max principal stress. In this case it's 392 for aluminum 6061. And then I want to look at aluminum 7050, and my max von Mises is 85. I mean my max principal is 85, excuse me. And then I want to get my von Mises, and it's going to be different wherever you go. This is just kind of how I do the analysis. 77 for aluminum 7050, and the reason I use the material tab is because a lot of times you have components composed of the same materials and it gets exhausting to go through and evaluate each component in an assembly. The material tab kind of cuts down that process when you have a large assembly. So I'll go put in 77. So now, since we use unit GLoads, we can go ahead and scale these to whatever desired GLoad we want. So if my boss came back and said, hey, look at a 6G downward load, essentially I would take my unit load stress, and multiply that by the GLoad multiplier factor. So I'm going to fill that in here. I actually want to freeze that, the GLoad multiplier, and I can change this to 6 GLoad, and it updates the stresses. And then also when you're doing this, you may have some temperature knockdown factors. In this case I'm using 90%, and I'm actually knocking down my my allowables, my yield strength, and my ultimate tensile strength. But that's subject to the environment. That's something you would have to do. And then you want to calculate your margins of safety for yield and ultimate. So in this case, my allowable for yield is going to be my knockdown yield strength. My safety factor for yield, I tend to use 1.15. And then my load, we want to use von Mises when we compare to yield. And I want to freeze the safety factor. Carry that down. We do the same thing for ultimate, except we compare it to the max principal stress, and we use a different safety factor. So I'm going to use my knockdown ultimate strength as my allowable, and then a safety factor of 1.5 is what I tend to use, and then the load, I'm going to use the max principal. And I want to freeze my safety factor here. You can see our safety factors are positive, which is great, but then again, you know, my boss comes back and say, oh man, I messed up. They want to look at a 15 G acceleration load, so I just update my GLoad scale factor, and it updates my margins of safety. I can go back to him and say, yes, this is great, this is still positive, and that really is a shortcut. Otherwise you'd have to go back in here to your Abaqus and go into the load and go edit your loads, and it's really cumbersome. You'd have to go in here and edit your acceleration, rerun the analysis, and that's not working smart, that's working hard. So that's how you run a GLoad analysis in Abaqus, and that's how you do some post-processing on some metallic materials. Of course, keep in mind this was just a demonstration of a quick workflow to run an acceleration load analysis. Of course, there's a lot of grunt work left that should be done in this case, such as mesh refinement and making sure the results make sense and eliminating any singularities that may exist. So just keep that in the back of your mind. All I wanted to show in this case was how to run unit GLoads for a linear analysis and post-process the results. And this, what I showed here, is how it would be done. So I hope you enjoyed the video, and I'll see you next time. Adios.